Hi everyone, Stuart here. In today's video we want to discuss moments and masses. Now, this is something you might know from physics. Obviously masses, we know what those are. Moments, do we know what those are? Well, a moment, it's quite hard to describe, at least for me it is. It's a mathematical quantity that tells us about rotationary properties of an object. So you could have a moment of inertia, which is what we'll later learn is the second moment. But today we're going to be talking about moments and masses. With single variable calculus, we could traditionally talk about it with a lamina, just like a line, kind of. Now with multivariable calculus, now that we have multivariable integration techniques, we can take it with any type of surface along an axis as opposed to just this axis here. All right, so let's discuss. So here are our equations that we want to know. Now our x moment is equal to the mass, or well, it's equal to the integral over the domain of our solid of y times our density. And then the yth moment, the yth first moment, is equal to the double integral of x times the density function. We can also define the center of mass as being x bar comma y bar, which is equal to the yth moment over the mass, and then the x moment over the mass. You can kind of see the switcheroo that we have here, obviously, because we have x and y components in our integrals that are swapped. Anyways, why don't we try an example here? So I'd like us to find the center of mass of the lamina, given that the lamina is a semicircle whose density is proportional to the distance from the center. So what do we have here? So we've got a semicircle. You see we're applying all of our polar stuff that we learned earlier. There's our semicircle, and let's say that we have a radius of a. And as a gets larger, our density is going to be proportional to that radius. So what we want to do is we want to find the center of mass of this. Now what we know is that because this is symmetrical, so the density here is going to be the same as the density there because they're the same distance out, our x center of mass is going to be at 0. So what we want to do is we want to find the y component of the center of mass, and that will tell us what the actual center of mass point is. So we can define our density function, noting that x squared plus y squared is equal to a squared. So we can define rho of x and y as being equal to some constant times our distance. We'll call that constant k. So now we want to find the mass. So the mass is something that we need to find before we can even find the moment and the y component of the center of mass. And we only want to find the y component. So mass is equal to the integral over density. So this is the integral of square root of x squared plus y squared dA. That's a double integral we don't want to need to do in Cartesian coordinates, so we switch it over to polar. So we get the integral between 0 and pi, obviously from sweeping from here over to there. Then we get the integral from 0 to a, sweeping our radius from here out to here. And we get kr squared dr d theta, obviously, because we put in that factor of r already. Now, because we have products of functions that are of their own variables, we can write this using that integral property, such that we get k times the integral from 0 to pi of d theta times the integral from 0 to a of r squared dr, which is equal to 1/3 pi k a cubed. It's an easy integral to do. So again, we know that x bar is going to be 0 because of symmetry, but now to find y bar, we take 1 over the mass of the x the moment, so 1 over m, the integral of y rho dA. So we get 3 over pi ka squared times the integral between 0 and pi, integral between 0 and a of r sine theta, kr r dr d theta. Obviously, y is equal to r sine of theta, so that's why we have that there. And we can separate this into products of functions. We get 3 over pi a cubed times the integral from 0 to pi of sine theta d theta times the integral from 0 to a of r cubed dr. Now this gives us 3 over pi a cubed times the negative cosine of theta evaluated from 0 to pi. Then times 1/4 r to the 4th between 0 and a, which gives us 3a over 2 pi. So this means that x bar comma y bar is going to be 0 comma 3a over 2 pi. So you've found the center of mass of a semicircular lamina with density proportional to the distance. So that is how we do that. In the next video, I want to look at moment of inertia. Then we're going to look at probabilities real quick, and then we're going to look at surface area. That's our last application of double integrals. Thanks for watching. We'll see you in the next one.